What if the universe itself is not still, but in constant flight, an invisible tide, carrying galaxies away like lanterns drifting across a boundless sea? The early years of the 20th century, such a thought was unthinkable. The cosmos was imagined as eternal and unmoving, a vast and unshaken cathedral where the stars burned forever in their fixed places. Even Albert Einstein, when his own equations of general relativity whispered of a restless universe, recoiled from the idea. To silence the instability, he introduced a delicate balancing term, the cosmological constant artificial force. To hold the universe still, like a hidden hand pinning the cosmos in place. He feared the alternative, that everything might unravel, but the universe does not obey comfort. The thin, cold air atop Mount Wilson in California, a telescope gazed into the heavens with unprecedented clarity. Night after night, Edwin Hubble measured faint smudges of light. The great nebulae charted their motions. What emerged was a revelation. Those galaxies were not fixed ornaments on a celestial dome. They were receding, each rushing away from Earth and from one another, as though space itself were stretching between them. It was not a simple scattering of stars, but the expansion of the very fabric in which stars are embedded. Hubble's discovery in 1929 overturned not only science, but philosophy itself. The cosmos was no longer eternal. It was alive with motion, woven with time, carrying within it the echo of a beginning. A truth both wondrous and terrifying had surfaced. The universe is not fixed, it breathes, it grows, and it drifts endlessly outward. And humanity, fragile witnesses, must ask what this restless expansion means for all that ever was and all that will ever be. The revelation of an expanding universe did not merely alter numbers in an astronomer's ledger. It cracked open the foundation of human understanding. For centuries, the cosmos had been imagined as a steady stage, a backdrop for the drama of stars and life. But with Edwin Hubble's measurements came an astonishing message. The universe was not fixed, but restless. Every galaxy was a traveler, carried by the invisible swell of space itself. The shock was immediate and profound. If the universe was growing now, it must once have been smaller. And if one rewinds that cosmic motion far enough, the galaxies do not simply approach one another, they converge. All space, all matter, all energy, compressed into an origin point. Beyond comprehension, this was not just expansion, it was evidence of a birth. The idea unsettled philosophers and physicists alike. A universe with a beginning meant a universe with a history, and perhaps with a fate. Infinity had long been a comforting, endless cosmos, requiring no origin, no edge. But Hubble's discovery swept that comfort aside. Expansion implied finitude, a clock with a first tick. The cosmos was no eternal cathedral. It was a story unfolding. And all stories invite the question of how they might end. Albert Einstein had already glimpsed this danger years earlier. When he first solved the equations of general relativity, the mathematics did not allow for a stable universe. Gravity, acting across cosmic scales, should have drawn everything inward. Yet his instincts recoiled from the thought of collapse, or expansion. To restore harmony, he inserted a corrective term into his equations, the cosmological constant, a subtle pressure counteracting gravity, holding the universe steady, balanced on a knife's edge. But nature is not so easily tamed. When Hubble's discovery reached Einstein, he reportedly muttered words that would echo through history. The cosmological constant had been his greatest blunder. The blunder was not in the mathematics, but in his mistrust of them. The equations had whispered the truth that the cosmos was dynamic, unfixed, alive with change. The physicist who had redefined space and time had flinched at the most radical implication of his own work. The revelation spread like fire through the halls of science. If the universe was expanding, would it always do so? Or would gravity, relentless and patient, eventually slow the flight of galaxies, draw them back together, and trigger a cosmic collapse? Theorists struggled with this newfound instability. The universe had become a question mark suspended in the dark, a balance of forces too vast for easy answers. The prospect of endless growth was particularly unsettling. A universe without limit in time meant that galaxies would flee ever farther. Stars would exhaust their fuel, and the cosmos would drift toward cold, irreversible silence. This heat death, as it came to be called, was not an explosion but a fading. The lights of creation would dim, not with drama, but with exhaustion. Others imagined the opposite, a big crunch, in which expansion would someday halt, replaced by collapse. The galaxies would reverse their journeys, hurtling inward, until all matter and energy merged once again in a catastrophic convergence. In this vision, the universe was not a straight arrow, but a heartbeat to expansion and contraction repeating forever. It was a more palatable fate to some, for it promised renewal, rebirth from death. But the data offered no comfort, only ambiguity. The scientific shock lay not only in the discovery, but in its consequences. An expanding universe was unstable by definition. It forced humanity to imagine time as a line, not a circle, and to accept that the cosmos itself might be temporary. It destabilized physics, for the laws of motion, energy, and space were now chained to a changing fabric. And it destabilized philosophy, for it asked questions older than science. If the universe has a beginning, what lay before? If it has an end, what comes after? In the decades that followed, the shock deepened as instruments refined their gaze. Observations of galaxy clusters, the mapping of the cosmic microwave background, and the study of distant supernova only reinforced Hubble's conclusion. Expansion was undeniable. The question was not if the universe was changing, but how. Would gravity reclaim its dominance, or was the cosmos condemned to drift apart forever? To confront this was to confront infinity in an unfamiliar form. The infinity of a timeless universe, but the infinity of separation. Galaxies accelerating away until their light could no longer reach us. The universe fragmenting into isolated islands of darkness. To imagine such a fate was to stare into an abyss of loneliness written into the structure of reality itself. This was the terror of instability. The realization that the cosmos was not a safe, eternal container, but a restless ocean, its tides. Driven by forces beyond understanding, humanity had long dreamed of permanence among the stars. Instead, science revealed impermanence woven into the very fabric of space. The universe was not bound, it was adrift. And in that realization lay both wonder and dread. Wonder at the majesty of a cosmos unfolding in motion, and dread at the possibility that its expansion may never cease. The shock had only begun. The first shock of an expanding universe did not end with Hubble's revelation. Instead, it opened a new battlefield of ideas in which cosmology itself was torn between competing visions of reality. If galaxies were receding, what story was the universe truly telling? Was expansion a temporary episode in an eternal cosmos? Or the scar of a singular beginning, an origin point written into every drifting star? In the mid-20th century, two rival models rose to prominence. On one side stood the Big Bang, championed by Georges Lemaître, a Belgian priest and physicist who dared to suggest that all of creation had once been compressed into a primeval atom. On the other side, the steady-state model, defended by Fred Hoyle, Hermann Bondi, and Thomas Gold, argued for a universe eternal in age and appearance. They proposed that as galaxies fled outward, new matter was continuously created, filling the void and preserving cosmic balance. To them, a beginning smacked of mysticism. They longed for an infinite stage, untroubled by origins. The debate was fierce, stretching from the lecture halls of Cambridge to observatories across the world. For decades, evidence seemed too fragile to declare victory. Expansion was visible, but its meaning was contested. Was it a fleeting phase, or the lingering echo of creation? The question demanded instruments more powerful than the human eye. Radio astronomy blossomed in the 1950s, turning the Earth itself into an ear pressed against the cosmic static. Great dishes rotated in silence, scanning the sky not for visible light, but for whispers at longer wavelengths, signals untouched by dust and distance. And then, in 1965, came an accident that would shift the course of science at Bell Labs in New Jersey. Arno Penzias and Robert Wilson worked with a horn-shaped antenna designed for satellite communication. Yet no matter how they tuned their instrument, a faint background hiss persisted, uniform in every direction. They checked for faulty equipment, for city interference, even for nesting pigeons fouling the dish. But nothing explained it away. Across the universe, a low murmur filled the void, a cosmic echo. At the same time, just miles away, Robert Dick and his team at Princeton were preparing an experiment to search for precisely such a signal. When the groups connected, realization struck. This was no noise. It was the afterglow of creation itself. The cosmic microwave background had been found. A relic of the infant universe, light stretched thin by billions of years of expansion. Here was the decisive blow against the steady state. An eternal universe could not explain a uniform bath of cooled radiation surrounding every galaxy. Only a hot, dense beginning could. The Big Bang moved from speculation to inevitability. Anchored now by observation, but discovery was only the beginning of deeper investigation. The microwave background was not silent. It was a tapestry, filled with patterns invisible to the naked eye. Later satellites, from Cobb in 1992, WMAP in 2001, would map its faint fluctuations, ripples, in the first light of the cosmos. These were the seeds of all structure. The fingerprints of quantum fluctuations, magnified by inflation, imprinted across the sky. What had been smooth became subtly textured, a record of the first instants etched in radiation. Meanwhile, Hubble's law was refined with increasing precision. Galaxies were no longer mere smudges, but measurable entities with distances tied to their recessional speed. As astronomical photography improved, vast surveys emerged, charting tens of thousands of galaxies. Patterns revealed themselves, galaxies, forming clusters, clusters joining into superclusters, and those into filaments, stretching across hundreds of millions of light years. Between them yawned voids, immense regions, almost empty, cosmic deserts, larger than imagination. Together, these structures formed the cosmic web, sprawling architecture that expansion had sculpted over eons. It became clear that expansion was not chaotic scattering, but an orderly unfolding governed by the delicate interplay of gravity and time. Where matter pooled, gravity wove galaxies together. Where matter thinned, expansion pulled space wide. The story of cosmic flight was one of tension, the universe balancing attraction and repulsion, clustering and dispersal. By the late 20th century, expansion was no longer a vague truth, but a measurable, quantifiable phenomenon. Astronomers could trace it across billions of years using quasars as beacons, supernova as candles, and the redshifts of galaxies as mile markers on the cosmic road. The universe was not static, not eternal, but a dynamic history, readable in light itself. Yet with every answer came new questions. Why were galaxies arranged in such vast webs? Why were the microwave backgrounds fluctuations so uniform, so fine-tuned? The deeper scientists peered, the more the universe seemed both knowable and impossible. Expansion was a fact, but its cause, its ultimate trajectory, remained elusive. This deeper investigation transformed cosmology into a discipline of precision. It was no longer speculation, but measurement. No longer philosophy, but data. Yet the emotional weight remained. To study the sky was to realize that humanity was watching a story written on scales beyond comprehension. A narrative measured in billions of years, where galaxies themselves were characters swept along by the current of space. The discovery of the cosmic, microwave background had silenced one debate, but it opened another. What forces shaped expansion, and what destiny did they demand? Cosmic Web spoke of gravity's artistry, yet the uniformity of radiation hinted at inflationary epochs still unexplained. Instruments grew ever more powerful, but the mystery only deepened. Expansion was not simply occurring. It was accelerating, evolving, hiding within it the fate of all that exists in this way. The mid-20th century was more than a chapter in scientific progress. It was the moment the universe revealed itself not as eternal stage, but as restless story. A story measurable, yes, but still unfathomable in its implications. Humanity now stood not in a static cathedral, but in a vast, expanding ocean whose tides carried galaxies like drifting lights. And the more closely those lights were measured, the more urgent the question became. Where was the current carrying them? Toward collapse, or into the silence of endless separation? The deeper the investigation went, the more profound the silence that followed each revelation. The universe had spoken, but only in whispers that invited still deeper listening. By the final years of the 20th century, astronomers believed they had glimpsed the arc of cosmic history. The universe, born in fire, was expanding still, but gravity, they thought, would one day slow its restless flight. Galaxies would recede, yes, but at a decreasing pace, their journeys checked by the inexorable pull of matter. Some expected the cosmos to drift toward a quiet equilibrium. Others foresaw a collapse, a cosmic rebound in which all would be drawn back together. The debate was fierce, but the framework seemed secure. Expansion was the stage, gravity the counterweight. The question was merely which would triumph in the long run. But in 1998, the universe delivered a revelation that shattered both predictions. Two teams, working half a world apart, set out to measure the rate of expansion with unprecedented precision. The Supernova Cosmology Project in California and the High-Z supernova, search teams scattered across continents both turned their telescopes toward a rare kind of stellar explosion type Ia supernova. These cosmic beacons erupt with extraordinary brightness, burning with nearly uniform intensity. By comparing their observed light to their intrinsic luminosity, astronomers could measure distances across billions of light years, turning the explosions into yardsticks for the universe. The expectation was simple. Distant supernova should appear, slightly brighter than anticipated if gravity had been slowing the expansion. But when the data arrived, the opposite was true. The ancient supernova were dimmer, not brighter. The galaxies hosting them had raced farther away than models allowed. The implication was inescapable. Expansion was not decelerating. The universe was not slowing its escape. It was fleeing faster, as though driven by an invisible wind. This discovery landed like thunder. Centuries of intuition insisted that gravity must pull back, that attraction was the fundamental tether of existence. Yet here was evidence of a force more powerful, one that did not bind but repelled, pushing galaxies apart with increasing speed. A universe already unmoored was now revealed as a runaway, its expansion spiraling beyond expectation. Physicists reached for a name and found one in an old idea: dark energy. A placeholder, a phrase as much as a theory, representing the unknown. Agent of acceleration. What it was, quantum vacuum energy, a new field, or something more exotic remained, cloaked in mystery. But its effects were unmistakable. It was not simply a nudge at the edges of physics. It dominated the cosmos. By current estimates, nearly 70% of the universe is made not of stars, planets, or galaxies, but of this dark energy. An unseen pressure woven into space itself. The image was staggering. Matter, the familiar substance of worlds and lives, accounted for less than a third of reality. All the galaxies ever seen, all the atoms ever measured, floated as islands in a sea of the unknown. The cosmos was revealed as not only stranger than imagined, but structured by forces beyond comprehension. The acceleration posed a new terror: isolation. As galaxies raced apart, the light from distant realms would eventually slip beyond reach. Redshifted into invisibility by the stretching fabric of space, in billions of years, observers in the Milky Way would look outward and see only their own galactic neighborhood. The rest of the universe vanished behind horizons of darkness. The great cosmic web would unravel into solitude, each cluster marooned. In the expanding void, this future, called the cosmic runaway, carried profound philosophical weight. The universe was not merely restless, but destined to scatter its contents irretrievably. The fabric of time itself seemed to hasten its own unraveling.
Sigh.
The stars of today's night sky were not eternal companions, but fleeting apparitions, destined to vanish from view, one by one. The strangeness lay also in the mathematics. According to Einstein's equations of general relativity, gravity should have been the master of cosmic destiny. Every particle of mass attracts every other, and over vast scales this attraction should counterbalance expansion. Yet dark energy bent those rules. Instead of pulling inward, space itself pushed outward, as if the vacuum was charged with a kind of negative gravity. The equations could accommodate such a force, but only by reintroducing the very cosmological constant Einstein had once dismissed. As a blunder, suddenly his discarded term returned from exile, not as mistake, but as possible truth. Still, the nature of dark energy eluded description. Was it a true constant, a fixed feature of the vacuum? Or did it evolve, waxing and waning with time? Could it be a manifestation of quantum fluctuations, the jittering foam of space-time at microscopic scales? Or was it something beyond known physics, an echo of extra dimensions, or a field yet unnamed? The answers remained out of reach, obscured, behind data too sparse to decide. What was clear was the defiance of intuition. The cosmos did not resemble a pendulum swinging between contraction and expansion. It resembled instead a balloon inflating ever faster, each patch of its surface rushing away from every other. No anchor held the universe steady. No brake slowed its momentum. Expansion itself was accelerating, indifferent to comprehension, unstoppable by any force known to science. To confront this was to feel the fragility of existence. Galaxies, once imagined eternal, were revealed as temporary neighbors. The night sky, once thought permanent, was a passing arrangement destined to dissolve. Humanity, so recent in cosmic time, had arisen at a fleeting moment when the universe was still young enough for its distant lights to be visible. To future eyes, that grandeur would be gone, erased by acceleration, leaving behind only darkness punctured by local stars. The escalation of discovery reshaped physics. Dark energy was not a footnote, but the dominant chapter of the cosmos. Presence forced a reevaluation of everything thought secure, from the ultimate fate of the universe to the very laws governing space and time. It was as though reality itself had turned unfamiliar, revealing that the forces of attraction and cohesion were but minor players in a larger, more enigmatic drama. Scientists probed the phenomenon with growing urgency. Observatories mapped the clustering of galaxies, searching for subtle patterns in their distribution. Satellites measured the cosmic microwave background with exquisite precision, tracing the fingerprints of expansion across deep time. Every dataset reinforced the conclusion: acceleration was real, and dark energy was its engine, yet none revealed its essence. For now, the universe remained a riddle, written in its own flight. The more it expanded, the less approachable its truth became. Galaxies sped away not only in distance, but in meaning, carrying with them the answers to questions left unasked by earlier centuries. In the silence between stars, one realization grew clear: the cosmos was not bound by expectation. It was outrunning even imagination. The terror of instability had become the terror of inevitability. Expansion was not slowing, nor would it pause. It raced forward, propelled by an invisible hand, promising a future where everything familiar would be scattered across an unreachable horizon. The universe, once conceived as eternal sanctuary, revealed itself instead as an accelerating exile, casting its galaxies adrift in a sea of ever-growing emptiness. And still, the expansion quickened. The revelation of acceleration was not an answer, but the opening of deeper riddles. If gravity no longer held dominion over the cosmos, what unseen agent commanded its fate? Astronomers and physicists turned to theory, weaving possibilities. From the fragile threads of mathematics and observation, each proposal illuminated fragments of truth, yet none dispelled the darkness entirely. The simplest explanation reached back to Einstein himself. His discarded cosmological constant, once a mathematical patch to preserve a static universe, re-emerged as a candidate for dark energy. In this vision, space itself possessed an intrinsic energy, a pressure that did not dilute as galaxies drifted apart but remained constant, woven into the very fabric of the vacuum. Unlike matter, which thins as it spreads, this vacuum energy persisted, and as the universe grew, its influence mounted, accelerating expansion without end. But the vacuum is no simple void. Quantum field theory describes it as a restless stage, filled with fluctuations, virtual particles appearing and vanishing in ceaseless play. If dark energy were the manifestation of this quantum froth, then acceleration was the echo of quantum mechanics imprinted on the largest scales of the cosmos. Yet calculations stumbled. The predicted energy of the vacuum, derived from quantum fields, exceeded observations by a factor so immense it defied imagination to the power of 120. The most extreme mismatch between theory and reality in all of science. The cosmological constant explained the data, but its origin remained a wound in physics, a glaring mystery hidden beneath elegance. Others envisioned dark energy not as constant, but dynamic, a new kind of field dubbed quintessence. Unlike the unchanging cosmological constant, quintessence could evolve with time, strength waxing or waning as the universe aged. Perhaps acceleration was not permanent but a phase, destined to shift into something else, slower expansion, collapse, or a still stranger transformation. Observations searched for clues, tiny deviations in the rate of acceleration, subtle differences in galaxy clustering. So far, none have been found. The universe accelerates steadily, offering no hint of change, yet speculation reached further, into possibilities more haunting. Some theorists proposed phantom energy, a form of dark energy, with properties so extreme it would not merely accelerate expansion, but amplify it endlessly. In this scenario, acceleration grows without bound, tearing galaxies apart, unbinding solar systems, treading planets, atoms, and even the fabric of space-time itself. This cataclysm, known as the Big Rip, paints a cosmos that ends not in silence but in disintegration. The calendar of existence would tick toward a finite horizon, where even the smallest particles dissolve into nothingness. Other visions extended not to endings but to multiplicities. If dark energy were linked to the mechanism of cosmic inflation, the rapid, exponential expansion believed to have occurred in the universe's first fraction of a second, then its persistence might imply something even grander. Inflation, once triggered, may never cease entirely. Regions of space may continue to balloon outward, spawning bubble universes within an infinite multiverse. In this eternal inflation, our cosmos would be but one bubble among countless others, each with its own laws of physics, each unreachable, sealed beyond horizons expanding faster than light can travel. The accelerating universe we observe would then be only a local detail in a boundless tapestry of universes endlessly budding from the EHL. Quantum foam. These speculations strained Einstein's relativity to its limit. General relativity described the geometry of spacetime with exquisite precision, tested from planetary orbits to the edges of black holes. But at the scale of the vacuum, in the marriage of quantum fields and curved space, the theory faltered. The mathematics of relativity and quantum mechanics refused reconciliation, leaving a gap where dark energy resided. Perhaps the true explanation demanded a new framework entirely, a theory of quantum gravity not yet written. The question deepened into philosophy. Does endless expansion imply an infinite universe, stretching without boundary, or only infinite growth within a finite whole? Its fabric expanding, yet its extent still circumscribed? If inflation and multiverse theories hold true, infinity multiplies universes proliferating beyond imagination, each isolated, each real, each invisible. The human mind falters at such magnitudes, unable to picture infinities nested within. Infiniteness, in the background, loomed the chilling prospect of heat death. If dark energy continued its steady hand, if expansion never ceased, the cosmos faced a future not of violence, but of exhaustion. Stars would burn their fuel and fade into white dwarfs, neutron stars, and black holes. Black holes themselves would evaporate through Hawking radiation, vanishing over unimaginable timescales. Galaxies would drift beyond sight, and eventually, matter would dissolve into a thin mist of particles scattered across an ever-growing void. The universe would reach maximum entropy, a state of perfect uniformity where no work could be done, no complexity sustained, no structure endure, a cosmos. Still expanding, but cold, empty, and silent forever. This fate, though abstract, carried profound weight. It suggested that meaning, beauty, and life itself existed only as fleeting arrangements, temporary islands in a sea destined to flatten into sameness. The lights of the night sky, so eternal to ancient eyes, were temporary sparks in a universe that would one day forget they ever existed. The heat death was not a violent apocalypse but a slow erasure, an eternal fading into darkness. Yet even here mystery remained. Could expansion evolve in ways yet unimagined? Could dark energy decay, transform, or reveal hidden structure? Might some undiscovered principle alter the trajectory, reshaping fate entirely? Science answered only with humility. The data showed acceleration, but not its cause. Each theory, vacuum energy, quintessence, phantom energy, eternal inflation, was a lens into possibility, but none offered certainty. The cosmos continued its flight, its reasons hidden beyond reach. Speculation itself became part of the human story, reflecting not only on the universe, but on those who asked. To imagine the Big Rip, the multiverse, or heat death, was to confront mortality on the grandest scale, the mortality of everything. Yet within that confrontation lay wonder. For to ask what dark energy is, to imagine the fate of expansion, is to reach for comprehension across the abyss, to demand meaning from the silence of the stars. The theories remained provisional, the speculations haunting. But they revealed a deeper truth, that the universe was stranger than even Einstein, Hawking, or any human mind could predict. It was not bound by permanence. It was a story without an ending, yet written, accelerating toward a horizon of mystery, and still, the galaxies fled outward, carrying with them the answers, receding faster than light can bridge. To ask what drives the universe to accelerate is to ask a question far beyond the scale of human senses. No naked eye could ever see galaxies rushing away. No unaided ear could ever hear the faint murmur of ancient light. To pursue such mysteries, humanity forged new senses machines that became our extended eyes and ears, stretched into orbit, planted in deserts, and scattered across mountaintops. These instruments were more than devices of steel and glass. They were expressions of longing, attempts to measure destiny itself. The Hubble Space Telescope was the first of these great witnesses. Launched into orbit in 1990, free from the distortions of Earth's atmosphere, Hubble's vision was sharp, enough to distinguish individual stars and galaxies millions of light-years away. It could track Cepheid variables, stars whose rhythmic pulsations revealed distances with reliable precision. By comparing those distances with redshifts, the stretching of light as space expands, Hubble refined the very scale of the cosmos. Later, by observing type Ia supernova, those stellar detonations so uniform they serve as cosmic yardsticks, Hubble anchored the distance ladder more securely than ever before. Its data not only confirmed expansion but mapped its rate with growing accuracy. Each orbit of Hubble was a reminder that space was not static, but stretching, carrying galaxies ever farther apart. Yet galaxies alone could not tell the whole story. If expansion was accelerating, its fingerprints would also be etched in the afterglow of creation. To trace those patterns, humanity turned to the cosmic microwave background, the faint radiation left from the universe's childhood when it was only 380,000 years old. In 2001, the Wilkinson Microwave Anisotropy Probe, WMAP, took up its post 1 million miles from Earth. For 9 years, it scanned the entire sky, measuring tiny variations in temperature fluctuations of just millionths of a degree. These ripples were the fossilized seeds of structure, density variations that gravity would later sculpt into galaxies and clusters. From them, cosmologists derived the balance of ingredients in the universe, a mere sliver of ordinary matter, a greater reservoir of dark matter, and the overwhelming dominance of dark energy. But WMAP was only the beginning. In 2009, the European Space Agency launched Planck, an even more sensitive observatory cooled nearly to absolute zero, its instruments tuned to the faintest whispers of radiation. Planck mapped the microwave background with resolution so fine, it captured the harmonic peaks of primordial sound waves, echoes of pressure oscillations rippling through the plasma of the infant cosmos. Its results painted a universe astonishingly precise in its simplicity. Flat geometry, 13.8 billion years of age, and ruled by dark energy. Yet Planck also revealed subtle tensions. The rate of expansion it inferred from the early universe did not match measurements made in the nearby cosmos. The Hubble tension, as it came to be known, suggested a hidden inconsistency either in our instruments or in the universe itself. Perhaps dark energy was not constant. Perhaps new physics lurked in the gap. Meanwhile, other tools probed expansion from a different angle. The distribution of galaxies across the sky is not random, but patterned, shaped by ancient sound waves frozen into matter as it cooled. These baryon acoustic oscillations, faint ripples in the clustering of galaxies, serve as a standard ruler imprinted into cosmic structure. By surveying millions of galaxies, astronomers could measure how this ruler stretched with time, offering an independent test of expansion.
Ow!
Projects like the Sloan Digital Sky Survey and the Baryon Oscillation Spectroscopic Survey revealed the cosmic web in vast detail filaments stretching for hundreds of millions of light-years. Knots of superclusters bound by gravity and voids yawning between them. Each map confirmed the same truth. Expansion is not slowing, but accelerating. Yet none of these instruments pierced the veil of dark energy's identity. They measured its effect, not its essence. Was it truly Einstein's cosmological constant, unchanging through eternity? Or was it quintessence, a field evolving with time? Could it be phantom energy, destined to intensify until the universe itself tore apart? The data, though precise, remained mute on the question. For every narrowing of error bars, the mystery only deepened. In 2021, humanity unfurled its most ambitious eye yet, the James Webb Space Telescope. With a mirror of gold-coated segments and instruments cooled to cryogenic silence, Webb was designed to see the earliest galaxies. Born in the first 100 million years after the Big Bang, by capturing their light stretched into infrared, it traced the infancy of cosmic structure. In doing so, it also extended the reach of the cosmic distance ladder, observing supernova and galaxies farther back in time than Hubble could. Webb's observations, combined with earlier data, began to hint at anomalies, galaxies forming faster. Then models predicted structures appearing unexpectedly early. If confirmed, these tensions could be clues that dark energy itself behaves differently across epochs, or that our cosmological models are incomplete. But Webb is not the final word. On the horizon stand even more specialized instruments, designed explicitly to hunt the fingerprints of dark energy. The European Space Agency's Euclid mission, launched in 2023, is tasked with mapping billions of galaxies, tracing weak gravitational, lensing and baryon acoustic oscillations to chart cosmic acceleration with unprecedented accuracy. NASA's Nancy Grace Roman Space Telescope, planned for the mid-2020s, will survey vast swaths of sky in infrared, its wide field enabling the detection of thousands of supernova and the mapping of large-scale structure across cosmic time. Together, Euclid and Roman promise to tighten the noose on dark energy's properties, whether constant, evolving, or something yet unimagined. Ground-based observatories join the effort. The Veracruz Observatory in Chile, with its 8.4-meter mirror and massive camera, will scan the entire southern sky every few nights, building a time-lapse movie of billions of galaxies. By measuring subtle distortions from gravitational lensing and tracking distant supernova, Rubin will add yet another layer of evidence. The Dark Energy Spectroscopic Instrument in Arizona is already cataloging tens of millions of galaxies, refining measurements of baryon acoustic oscillations. Across deserts and mountains, these observatories form a chorus, each voice tuned to a different note of the cosmic song. Yet even with this arsenal, the struggle persists. Physicists wrestle with the same haunting questions. Can these instruments distinguish between a true cosmological constant and a dynamic field? Can they detect whether dark energy evolves, or whether its pressure is stronger than -1, hinting at phantom energy? Can they reveal cracks in general relativity itself, signs that Einstein's framework must give way to a deeper theory? Race is not merely for data, but against time itself. For as expansion accelerates, galaxies recede beyond horizons, their light lost forever. Evidence is slipping away, erased by the very phenomenon we seek to understand. Humanity investigates the universe in a fleeting window, when the cosmic web is still visible, when supernovae still shine in distant galaxies, when the afterglow of creation can still be measured. Future astronomers, in a far older cosmos, may see only emptiness, the clues of dark energy gone beyond reach. Thus, the tools of cosmology are more than machines. They are acts of defiance, fragile human constructs hurled into the void to wrest meaning from inevitability. They confirm that the universe accelerates. They refine the parameters of expansion. They whisper of dark energy's dominance. Yet they do not reveal its nature. The cosmos remains silent on that point, as though guarding its final secret in the glow of Hubble's mirrors, in the frozen detectors of Planck. In the golden hexagons of Webb, one truth resounds. Humanity has glimpsed its own fate. Expansion. Is the script written into space-time? Acceleration, the punctuation of its trajectory? The instruments do not end the mystery. They sharpen it. They show not an answer, but a riddle more precise, more haunting, more urgent. The universe continues to flee, galaxies rushing outward on an unstoppable tide. The tools humanity has built trace that tide with exquisite care, but they cannot halt it. They measure, they map, they predict. But the current carries all things onward into the widening silence. And still, the instruments look up, waiting for the universe to speak again. If the universe continues to expand forever, then all of existence is already set upon a path toward futures both wondrous and terrifying. These futures are not myths or allegories, but projections born of physics, extrapolations of the same. Laws that govern stars and atoms. They are not predictions with certainty, but possibilities sculpted from data, each carrying its own haunting poetry. And together, they reveal what eternity may truly mean when applied to space and time. The first of these visions is the Big Freeze. In this scenario, dark energy remains constant, driving galaxies apart faster and farther until isolation becomes the universe's defining feature. With every passing billion years, more galaxies slip beyond reach, their light stretched into invisibility by the accelerating expansion. The night sky, once alive with stars, grows emptier. Civilizations in the distant future, if any endure, would gaze upward and see only the fading glow of their local cluster. The cosmic web itself would dissolve into loneliness. Time in such a universe becomes a slow unwinding of energy. Stars exhaust their fuel, burning into red giants, collapsing into white dwarfs, or exploding into supernova. The galaxies, once vibrant with star formation, grow quiet as their gas is consumed. For trillions of years, the last stars flicker, until only degenerate remnants remain. Cold dwarfs, neutron stars, black holes. Even these are not eternal. Black holes, by the strange mechanics of quantum theory, radiate away their mass through Hawking radiation. Over inconceivable spans, far longer than the age of the current universe, they evaporate, vanishing into the void. What follows is the entropic end, heat death. The universe, still expanding, reaches maximum entropy, a state of perfect uniformity. No gradients remain to power stars, planets, or life. All motion flattens into randomness. The cosmos does not collapse in fire or chaos. It simply fades, a silence stretched across eternity, an ocean of particles drifting forever in infinite night. In this vision, expansion is not destruction, but erasure, a dissolving of meaning into sameness. It is a future not of violence, but of stillness without return. Yet there is another, more violent possibility, the Big Rip. If dark energy is not constant, if its strength grows with time, then acceleration itself could become catastrophic. In this scenario, expansion does not merely separate galaxies. It accelerates without limit, tearing structure apart at every scale. First, galaxy clusters unravel, their bonds severed by space's relentless push. Then galaxies themselves are torn asunder, stars drifting free. Later, solar systems are pulled apart, planets ripped from their orbits, moons flung into the dark. As acceleration grows, even stars and planets lose cohesion, torn into their constituent atoms. Finally, as the critical moment arrives, molecules, atoms, even the nuclei of matter themselves are ripped apart by the runaway expansion of space. The Big Rip is a universe annihilated by its own restlessness. It's the fabric of space-time stretched until it can hold nothing. Unlike the cold silence of the Big Freeze, this end is violent, a crescendo of destruction in which all bonds are broken. Yet both arise from the same cause, expansion unending, dark energy dictating a future beyond the grasp of gravity. Beyond these fates lies a still stranger vision, eternal inflation. If the mechanism that drove the universe's earliest exponential expansion never fully ended, then even now, while our cosmos expands, other regions may continue inflating beyond our horizon. In those regions, bubble universes bud into existence, each with its own laws of physics, its own particles, its own possibilities. Our universe, vast and ancient, would be but one bubble in an infinite froth. One story among countless others, forever branching in an endless multiv. Foreserved in such a scenario, expansion never ends because creation itself never ends. Space continues to blossom, eternally spawning new realities, unreachable and unseen, each forever isolated by the accelerating growth between them. Eternity here is not silence but proliferation, a branching infinity of universes. Yet the terror is no less profound. If infinite realities exist, then meaning dissolves into multiplicity. Everything that can happen does happen, endlessly. The uniqueness of our own universe, of our own lives, would vanish into infinity's indifferent repetition. What unites these visions, the Big Freeze, the Big Rip, eternal inflation, is the same haunting prospect, eternity without cycle. In the mythologies of ancient cultures, endings were often followed by renewal. Death gave way to rebirth, collapse to creation. But expansion without end leaves no room for renewal. It offers no circle, only an arrow stretching into forever. If the Big Freeze comes, the universe drifts into silence without return. If the Big Rip arrives, it destroys all bonds irreversibly. If eternal inflation reigns, universes multiply without end, but none return to the beginning. Eternity is not a cycle of renewal, but a progression toward outcomes from which there is no return. The philosophical terror of such eternity is profound. Human minds are shaped by cycles, the rising and setting of the sun, the turning of seasons, the beating of hearts. To imagine time as unending drift without repetition is to confront a form of infinity alien to experience. It suggests that everything, once gone, is gone forever. Stars will not rise again. Galaxies will not return. Existence fades and does not reappear. And yet, within this terror lies wonder. For the same expansion that promises silence also gave birth to the cosmos we inhabit. Without it, galaxies would not have formed, stars would not have burned, life would not have emerged. The very instability that condemns the universe to eventual emptiness also granted it richness, beauty, and time. The night sky, dazzling and fragile, is possible only because expansion carries it forward. The question is not only how the universe will end, but how it has already unfolded in ways that allow consciousness to ask the question at all. What does forever mean when applied to space and time? It is not a word that human intuition easily holds. Forever in the cosmic sense is not decades, not millennia, not even billions of years. It is spans of time that dwarf imagination, time enough for stars to burn, black holes to evaporate, galaxies to vanish, and still only a fraction of eternity will have passed. Forever means that whatever path expansion takes, freeze, rip, or proliferation, it will not reverse. It will continue without end, carrying existence into horizons we cannot. Yet conceived in this way, expansion is both gift and sentence. It ensures that the universe is dynamic, alive with structure and history, but it also ensures that history leads to outcomes beyond recovery. The futures are speculative, but their poetry is the same. A cosmos running away from itself, leaving behind the fragile lights of its youth, scattering them into the silence of eternity. And so, if expansion never ends, the universe becomes both cradle and grave. A place where beauty is fleeting, where meaning is carved against the certainty of dissolution. Its final lesson may not be one of despair, but of perspective, that to exist in such a universe, even briefly, is to witness the rare moment when the sky is still full, when galaxies are still visible, when the questions can still be asked. For in the endless future, when expansion has carried all light beyond reach, no eyes will remain to wonder, no voices to speak. Only now in this fragile age can the universe reflect on itself before silence falls. The universe expands, and with every measure of distance gained, humanity is reminded of its fragility within this restless sea. Galaxies drift apart, light grows thin, and the cosmos unfolds with a scale that dwarfs every history ever told upon a single planet. Against that backdrop, the lives of civilizations are but sparks, brief and fragile, ignited within a darkness that cares nothing for permanence. And yet, those sparks have become eyes that see, minds that wonder, voices that ask what it all means. This paradox lies at the heart of cosmic reflection. Expansion guarantees insignificance, for it stretches reality to scales beyond comprehension. The Milky Way is but one galaxy among trillions, each a fleeting congregation of stars drifting towards solitude. Earth itself is smaller still, a mote orbiting an ordinary star in a spiral arm scarcely noted by the whole. On cosmic scales, the planet is invisible, its inhabitants negligible. Yet it is precisely here, upon this speck, that awareness has arisen, awareness of the very expansion that consigns us to irrelevance. It is as though the cosmos, in scattering its galaxies, has also gathered itself into a single fragile perspective, one that can recognize the immensity of what unfolds. In that awareness lies meaning, however fleeting. The expansion of the universe does not diminish the value of human thought. It magnifies it. To exist in a cosmos that grows cold and empty, to witness the rare era when galaxies still fill the sky, is to hold a privileged moment. This is the age when the cosmic web can be traced, when the afterglow of creation still glimmers in microwave detectors, when acceleration can still be measured before it erases its own evidence. Future eyes, if any remain, will look outward and see only darkness, the great structures already carried away. But here and now, in this fragile epoch, the truth is visible, and the questions can still be asked. Impermanence is the thread woven through all things. Stars die, galaxies scatter, and the universe itself drifts toward endings, both silent and violent. Expansion ensures that nothing lasts. But impermanence does not erase significance. It gives rise to it. Meaning emerges not from permanence, but from awareness within impermanence. A fleeting glance at the night sky, a life lived beneath its stars is no less profound because the stars themselves will one day fade. It is more profound, for it is finite. The value of light lies in its eventual loss. The weight of existence lies in its brevity. Science, in revealing expansion, has not offered comfort. It has stripped away illusions of eternity, replacing them with trajectories toward silence. But within that stark revelation is a kind of clarity. The universe is not a sanctuary immune to change. It is a story unfolding without pause. To know this is to confront fragility directly, to accept that everything dissolves, and yet to recognize that dissolving does not erase wonder. Awareness itself is the answer, the fleeting presence of consciousness within an expanding void. Perhaps This is the final lesson of expansion, that significance and insignificance are not opposites, but twins. Humanity is insignificant in scale, yet significant in awareness. Expansion renders the cosmos inhospitable, yet it is the very expansion that allows galaxies, stars, and planets to exist. It carries within it the seeds of both erasure and creation. It diminishes permanence, yet it makes possible the fragile moment in which life can ask its questions. The horizon of the future is haunting. Whether the universe ends in heat death, in a rip of space-time, or in an eternal proliferation of unseen, universe's all paths lead beyond return. Eternity here is not a circle, but an arrow. And yet, within that arrow lies the moment now, the fleeting present, when awareness exists. Eternity is not for us to hold, but the present is. And the present is enough. The night sky is filled with galaxies receding on invisible currents, their light already billions of years old. To look upward is to see into the past, to witness the slow drift of the cosmos toward a horizon beyond reach. It is also to witness beauty fragile and permanent, and yet real. Expansion may erase it in the future, but it grants it in the present. The universe expands, and so does wonder. And perhaps this endless unfolding is not a death sentence, but an invitation. An invitation to question, to imagine, to feel, to exist. To recognize that even in an indifferent cosmos, meaning is not. Given it is created in every act of awareness, every gesture of understanding, every reflection upon the stars. Expansion carries galaxies away, but it also carries thought to new horizons. Imagination to new scales, awareness to new depths. The universe expands, and with it, so does the possibility of wonder. It unfolds without end, and within its unfolding, humanity finds its place, not as masters of permanence, but as witnesses of fragility. The cosmos runs away from itself, yet in its flight it has given birth to eyes that see, to minds that reflect, to beings that can know they are part of something larger. That, perhaps, is enough. And so, the universe continues its acceleration, galaxies drifting outward on an unstoppable tide. In the silence that follows, one truth lingers. The cosmos expands, and so does the capacity to marvel.
The fleeting spark
Of awareness is fragile, but it is also luminous. It is the universe, reflecting on itself before the darkness comes.